Shop the Plato's Closet Black Friday event in North Charleston and West Ashley and let the deals begin. You know Plato's Closet always has a huge selection of trendy recycled styles at amazing prices, but Black Friday deals are different. They're better. We've been holding back some of our best inventory, and you won't want to miss our Black Friday event. Save on gently used styles from Patagonia, Lululemon, Lilly Pulitzer, and hundreds of popular brands. Plato's Closet is ready to let the Black Friday deals begin. Plato's Closet, located in West Ashley on Sam Rittenberg Boulevard and North Charleston on Rivers Avenue.
Hi there, thanks for joining us. This is Space Nuts. I'm your host, Andrew Dunkley. Hope you can stick around. We've got a lot to talk about today. What time is it on the moon? It's moon time. Could be daytime, could be nighttime. Depends where you are, but we're talking about real time. That we'll elaborate shortly. There might be a new way to find Planet 9. We're going to look at some sun rays on Mars and the dark Big Bang Theory. We'll also be answering some audience questions and much, much more on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me to hash all of that out with a hash brown in hand is Fred Watson, astronomer at large. Hello, Fred.
Yeah, hash brown would go down really well, actually, just now. Thank you for mentioning it. Yes,
I absolutely love them. I know they're a heart attack for breakfast.
Yes, quite so.
Yeah. Welcome back to the real world in the same time zone as me. Are you still suffering from jet lag after your sojourn to Europe?
It's not been too bad, thanks, Andrew. I did hit the wall at 9 o'clock for a couple of nights after the 9 p.m., I have to say, not 9 a.m., which would have been difficult. But, it's pretty good, thank you. So far, so good.
Excellent. Good to hear.
Oh, and there's Muscat just tripping in.
Oh, Muscat. We've never heard from Muscat.
Wow, well, he's kind of looking for somebody. Sure,
yeah, probably not you.
Yeah, not me.
Well, it's nice to hear from Muscat. Now, we've got a lot to talk about. What time is it on the moon, Fred?
It's probably hash brown time, mostly. So this is what's prompted this piece of research or investigation that's actually going on. I think it's being led from Europe, but includes pretty well all the world's space agencies. So I think the idea is, how do you define time on the moon? Do you have lots of different time zones like we have on Earth, or do you have a single lunar time zone? How does it all work? And how do you deal with nuances like the fact that the moon is a much less massive body than the Earth? It only has 1/80th of the mass of the Earth. Yeah. And so the relativistic gravitational time dilation on the moon is different from what it is on Earth. So there's a very, very tiny difference amounting to microseconds between the way clocks tick on the moon and the way they tick on Earth. But the story kind of starts really with the fact that over the history of our exploration of the moon, every space mission that's gone to the moon has basically set up its own time system, and usually they use the time back, mission headquarters, wherever that might be. No. And that's clearly not going to work if you've got many experiments going on the moon, perhaps many simultaneous missions on the moon, where you might have a permanent base on the moon. And so, I
can imagine that the Americans have set up a base and the Russians set up a base. That we'll have a meeting at 7 o'clock, but they're using different times. So,
exactly. So you've got to.
They've got a history of not keeping up with the world on time. They stuck with the Julian calendar a lot longer than everybody else.
That's true.
We switched to the Gregorian calendar.
We were pretty slow at that in
in Britain.
Yes, 1752.
Is that the famous case of where there were like 11 days lost and all those people got upset because they thought they were going to die or something?
Give us back our 11 days. That's exactly what happened. Yes, I can't remember the can't remember the dates when the change was made, and I should do because I've given talks about this stuff in the past, but it's a long time ago. But yes, 1752, there was a general election about the same time, and that became a hot topic in the election. The election material.
We're talking about a time where people still sort of didn't understand the whys and wherefores of things, and they thought that taking those days away would cause
shorten their life.
Shorten their life by 11 days or whatever it turned out to be.
And the government had stolen it. Yeah, it's a good story.
Same as having your spirit stolen when your photograph is taken.
That's along the same lines.
Yeah. It's a fascinating story. If you want to look it up, it's on Wikipedia and a bunch of other websites. It's a really fascinating story about those catch-up days back in the day. Back in the day,
that's right. And of course, that same time system spread to Australia by nefarious means, I'm sure. But coming back to the moon,
where we were,
there's essentially a set of discussions going on to basically to nut out an architecture that will oversee communications on the moon, navigation services on the moon, and part and parcel of that is time. It's being called LunarNet, LUNANET, all one word, a bit like Space Nuts is all one word. LunarNet is the architecture that is trying to be agreed. And a comment from Xavier Ventura Travesse, who is the European Space Agency's Moonlight Navigation Manager, who's coordinating the European Space Agency's contribution to LunarNet. Xavier says, LunarNet is a framework of mutually agreed upon standards, protocols, and interface requirements allowing future lunar missions to work together, conceptually similar to what we did on Earth for joint use of GPS and Galileo. Now, in the lunar context, we have the opportunity to agree on our interoperability approach from the very beginning before systems are actually implemented.
Hello, Marnie. Marnie's dropped in with you. Is that your coffee?
Thank you, Marnie. Told you they might get a coffee.
Yeah.
That's great.
There you are.
Thank you. So that's basically what's happening. In fact, there's another comment from an ESA navigation systems engineer, Pietro Giordano, who says timing is the crucial element. During this meeting, we agreed on the importance and urgency of defining a common lunar reference time, which is internationally accepted and towards which all lunar systems and users may refer to. A joint international effort is now being launched towards achieving this. And that's really what this story is all about. It's about people talking about how we set up time on the moon.
I'm just going to ask what may be a dumb question, but why can't they just go with Zulu time or international time?
Well, my guess is that that's what will happen, that it will be UT.
I've solved it.
You solved the problem, yeah. UT1 is the universal time system that is agreed upon on Earth, and it comes from the International Bureau of Weights and Measures in Paris. That's, I think, the organisation that coordinates it all. But the issue, though, is that if you've got like lunar GPS systems and things of that sort, which, by the way, some radio astronomers take a pretty dim view of because they want to put a radio telescope on the far side of the moon, where you're immune from radio contamination from Earth. If you put GPS satellites in orbit around the moon, well, you've kind of ruined that to start with. Yeah. Anyway, the issue is that if you're looking at really precise lunar timing, you have got this issue of the gravitational time dilation on the moon. There is a figure, which I haven't checked this, but it may well be about right. Because the gravitational potential on the surface of the moon is less than the gravitational potential on the surface of the Earth, the clock on the moon is going to run faster than one on the Earth by about 56 microseconds per day. And that is significant. That is really significant because GPS systems rely on nanoseconds. They've got to be accurate to far better precision than that. Yeah. So you can't. So that's really the answer. The counter answer to your suggestion. You can't just import terrestrial time. You've got to tweak it in some way.
You could if you could just make a clock that runs 0.56 microseconds faster, couldn't you? Just change the speed of the clock.
Yes, that's right. So you've got, but then you've immediately got something different from UT1. You can't just import it. You've got you can use it as the basis, but you've got to tweak it to allow for the low gravitational field. So all of this sort of thing is clearly what these people are talking about.
No wonder we committee.
Yes, that's right. It's if in doubt, form a committee. It's what you do.
That's right.
They even did that when Hans Lippershey turned up with the first telescope in The Hague.
Really?
Yes, indeed. In 1608, they formed a committee. That's what everybody does. Anyway, there is a nice final comment from Xavier, who I mentioned earlier. Throughout human history, exploration has actually been a key driver of improved timekeeping and geodetic reference models, which is a really good point because exploration is what drove the invention of the chronometer, the Harrison chronometer and all of that stuff, so that you can find your way properly.
Yeah.
And he goes on to say, it's certainly an exciting time to do that now for the moon, working towards defining an internationally agreed timescale and a common selenocentric reference, which will not only ensure he likes this word, interoperability between the different lunar navigation systems, but which will also foster a large number of research opportunities and applications in cislunar space. There you go. That's the words from the top.
Who would have thunk it was so complicated to tell time on the moon?
Well,
although it gives me an opportunity to razz my brother who, when growing up, couldn't understand how he was older than our sister because she was born in April and he was born in July. So how could he be older? He didn't get the concept of years.
Oh, that's interesting. Yeah.
Yeah, it's always funny just hearing him try to figure it out.
Well, yes. Yeah.
All right. So moon time is yet to be established. Something that they may establish is a new way to find Planet 9. What's that?
Well, I like this story.
We're going to look with our eyes.
Yeah, that's the problem. That's what we've been doing so far.
It doesn't work.
It's it is an issue that goes back. You and I have talked about this several times before, but not recently, which is why I thought it was a nice story to cover. The idea, of course, that there are several, and it's quite a large number, of the objects, the icy asteroids out there in the Kuiper Belt beyond the orbit of Neptune, whose highly elongated orbits seem to align. It's a particular cluster of those objects, and so they all, their orbits are all aligned in one direction.
Wow.
Now that's been disputed in more recent papers. What has been suggested is that that's just a selection effect. We're seeing that because we're only looking at the brighter objects. And, if you look at everything or you look at the whole cloud of Kuiper Belt objects in orbit around the sun beyond Neptune, you're going to find that thing disappears. However, the proponents for Planet 9 are confident that they are correct, that this curious alignment of the orbits is being caused by something that has not yet been discovered. And the suggestion is it's an object 5 to 10 times the Earth's mass. And I think, if I remember rightly, something like 4 times the diameter of the Earth was suggested, but that depends on its density, of course. So 5 to 10 times the mass of the Earth is the critical bit. And that's led to it being called Planet 9, which has upset some other people who think Planet 9 is Pluto, but
yes,
the international astronomical community doesn't think that is the case. Anyway, how do you discover Planet 9? Well, looking for it doesn't seem to have worked.
No.
And part of the reason is that the position where it's most likely to be is slap bang in the middle of the Milky Way. And so it's really, it's hidden among gazillions of other stars. You're looking for something whose distance is, if I remember rightly, it's thousands of times the distance of the Earth from the Sun. So way, way out there in the depths of the solar system. You have to look for its motion to identify that it's not a star. And things at that distance move very, very slowly through space. So this suggestion, though, comes from Manho Chan, who is an associate professor in the Department of Science and Environmental Studies at the Education University of Hong Kong, who's written a paper called "What If Planet 9 Has Satellites?" and follows through some of the tricks that might bring for would-be discoverers of Planet 9. So the theory goes, if you have satellites of a planet like Planet 9, as they orbit it, if they're in orbits that are anything but perfect circles, they will be heated by tidal interactions. And this is kind of what happens to particularly Io in orbit around Jupiter. That's squeezed and squashed by the gravity of Jupiter as it orbits. And that is why its temperature is high enough to make it the most volcanically active body in the solar system. It's erupting all the time. So this same idea, if you apply it to Planet 9, what you've got is essentially heating that is variable as the satellite goes around its planet. That heating, it changes, or the temperature of the satellite changes throughout the orbit around its parent body, which in this case is the hypothetical Planet 9. And that change is something that could be detected. And so rather than looking for desperately slowly moving objects in the Milky Way, what you look for is objects which are changing relatively rapidly, a heat signature, you could put it that way, that's changing more rapidly than what you would expect from any other object in the background. It would be a variable object. And moreover, the author of this paper has pointed out that there is one telescope on Earth which would be eminently capable of detecting that at this enormous distance from Earth, and that is ALMA, the Atacama Large Millimeter Submillimeter Array, up there in the heights above San Pedro de Atacama at 5,000 meters, and operated by actually a sort of it's three different organizations that operate ALMA, but one of which is the European Southern Observatory, which of course is very close to our hearts here in Australia because of our strategic partnership. So this author is suggesting we should get ALMA onto looking for satellites of Planet 9, which is an extraordinary idea. So
fascinating thought, except what if it's not a planet? What if it's a body of smaller objects, which is another theory as to what might be causing those gravitational effects?
That's right. There are a number of, a planet-sized black hole is another one that's been suggested.
Right.
But even such a weird and wonderful object as that might have satellites. That's the idea. If the Planet 9 or the Planet 9 proxy, whatever it is compact enough and has satellites around it, then the tidal effects will still exist.
All right. So it's just an idea as to how we should look. That's not actually happening as yet.
Sadly, no. But it might go on the wish list for Planet 9 pundits, and you never know. It might happen. By that, I mean somebody might apply for time on ALMA to do this, and that could do the trick.
The other reason it's called Planet 9 is because when you ask the question, have they found it? The answer is 9.
It would be in Munich, where it was last week.
2 weeks in a row we've had to use German gun.
Yes, we have. We're getting messages about it as well.
Yeah, in tweets.
Yes, that's right.
No idea. All right. This is Space Nuts with Andrew Dunkley and Professor Fred Watson. Let's take a little break from the show to talk about our sponsor, NordVPN. Well, I've actually just renewed my subscription to NordVPN, and I did it via the Space Nuts deal. I don't get a special deal. I get the same deal as you, and I decided to go the whole hog. So I went in to nordvpn.com/spacenuts, and I clicked on the Get the Deal button. And don't forget, there's a 30-day money-back guarantee. And I decided to go with the 2-year deal and get everything. So I've got the secure high-speed VPN, the malware protection, the tracker and ad blocker, the cross-platform password manager. I absolutely love that thing. Gosh, I've got over 300 passwords. How the heck are you supposed to remember all that? These password managers are brilliant. It saves you a lot of time and heartache. The data breach scanner, that's great. I found some vulnerabilities. And on top of that, I added the 1 terabyte of cloud storage and the next generation file encryption. Now, at the moment, you can get a deal where you get 1 month for free, and the first 2 years will cost you a lot less as a Space Nuts listener. So if you want to get that deal, and you can do it in monthly installments, 1-year plans, 2-year plans, but the longer you go, the cheaper it is on a month-by-month basis. And let's face it, for a few dollars a month, you're buying yourself a lot of peace of mind with VPN security and all the other bits and bobs that come with an account with NordVPN. I'm very, very happy with them, and I feel incredibly secure knowing that no matter where I am or what I'm doing, no one can get near me. So check it out today, nordvpn.com/spacenuts. Click on the Get the Deal button and choose the product that suits you best. It is well worth it, a small price to pay for keeping yourself safe. nordvpn.com/spacenuts. Now, back to the show.
3, 2, 1.
Space Nuts.
Now, we're going to talk about sun rays on Mars. This has been a rather amazing photograph that's been sent back by the Curiosity rover. It also dovetails well with a photo that was sent to me by Rusty in Donnybrook of a similar situation looking out from his place in Western Australia. And he was asking why the sun sort of split up into rays. And the answer on Earth is dust. And sort of only letting through the rays of red light because the dust had scattered all the other colours in the spectrum, something to that effect, if I'm remembering it correctly. But it doesn't look the same on Mars. It's a different effect.
Yeah,
maybe for the same reason, but a different effect.
Yeah. So you're right about the sunlight being red when it's really down on the horizon. Sometimes it's dust, but actually the molecules of the atmosphere also scatter light. So the blue light scattered out, and we see this predominantly red light. Now, I'm not sure what Rusty was sending you, but when we get this phenomenon, and it's everybody's seen it, the phenomenon of light, sunlight being sort of separated into individual rays by clouds blocking our view of the sun, and you combine that with a dusty atmosphere, then you get these rays of light, the shafts of light that are so obvious at sunset. They've got a technical term. They're called crepuscular rays. Crépuscule is a French word meaning evening or twilight, and so they're very common, and I find them fascinating. Sometimes, and I've only seen this once, and it was not very far from you, where I used to live in Terry Hills in northern Sydney. I saw those rays going right across the sky, all the way from the setting sun on one side to the opposite, what's called the antisolar point on the other side. And occasionally you will see that, and occasionally you'll see what look like rays. If you've got your back to the sun, you can see rays sort of coming out from the point exactly opposite the sun, and they're called antisolar crepuscular rays. And actually, there's a picture of them taken by Marnie some years ago in my book Cosmic Chronicles, or what's it called in America, Exploding Planets and invisible stars. That's right. There's a nice colour picture of those antisolar crepuscular rays. But cut to the chase, we now have a lovely image from Curiosity, the other rover on Mars that's still going strong, of crepuscular rays on Mars. And it's a phenomenon that has been expected but has never been seen before. And this is after sunset. And so what you've got is these rays of light, and they're blocked into rays by clouds that are blocking the sunlight below the horizon.
Yeah.
So it turns the light, instead of being a fan of light, it turns it into these individual streaks of light. But they too are lighting up thin clouds in the sky above Curiosity, and that's why they show up, the crepuscular rays. I think it's something that we might expect down the track from some rover on Mars to see the antisolar crepuscular rays that I've just been talking about as these shafts of light meet on the other side of the sky, an effect of perspective. Of course, the whole thing is due to perspective because these shafts of light are actually parallel. It's the sun's light is parallel rays because the sun is so far away, and as it blocks as the clouds block bits of it, so you get just individual shafts of light. They look as though they're streaming from the sun itself. A very evocative image, but they're actually parallel.
Yeah, and yet, being after sunset on Mars, it's not the kind of red you see on Earth. It's a very different.
Sunsets on Mars are blue.
Yeah,
and that's because the sky, the daytime sky on Mars is pink, and the sunset sky is blue, and it's the opposite way around from what we expect on Earth.
Yeah,
and that's because the dust particles, such a large amount of suspended dust in the Martian atmosphere. The dust particles are bigger than the molecules of air that scatter sunlight on Earth, and so there's a different scattering process takes place, and that's why you've got a pink sky.
Yeah, looks amazing. If you want to look at that image, it's on the phys.org website. It's quite pretty. I'll say pretty. And yeah, sun rays on Mars. If you do a search for that, you should be able to find it. Now to another story. Gee, we're jamming it in today, aren't we?
Jamming's the word.
Yeah, and it goes back to something that we get a lot of questions about, and I think we got a couple of questions about it last week, and that is the Big Bang. Now they're saying our universe may have been started by a dark Big Bang. What's a dark Big Bang?
Well, it's the suggestion.
Anyway, wasn't it at the beginning? Or we don't know. But biblically it was.
It was. So the Big Bang itself was not dark, and we know that because we can still see it.
Yeah, right.
In the cosmic microwave background radiation. That's the Big Bang. The light of the Big Bang redshifted to be 1,000 or 1,500 times longer wavelength than it was when the light left.
Well,
this is really trying to understand how dark matter came into being, because the current theory suggests that the Big Bang created space-time and matter, and at first it was just pure energy, but that pure energy, I think when the universe was something like 15 to 20 minutes old, it kind of condensed into protons and neutrons in a period which has the technical term of the Big Bang nucleosynthesis, and it's one of the reasons why we believe the Big Bang, because when you do the theory of how this Big Bang nucleosynthesis would work, you get exactly the amount of hydrogen, helium, and some lighter elements. I can't remember what they are actually. It's lithium one. I think there is a lithium issue. Anyway, those lighter elements basically are exactly what we find in the universe is what's predicted by Big Bang nucleosynthesis, which is one reason why the Big Bang theory is so well established. However, what we can't understand is where the dark matter came from. I mean, we don't know what dark matter is. We know it's some form of subatomic particle, and there's a very good reason for believing that. but it makes up the majority of mass in the universe. And so most theories of the Big Bang assume that whatever the process was that generated the particles themselves, the particles that we can see or detect, also created dark matter. And after and the dark matter then really didn't do much. It was just there, not interacting with anything else. But this is this new idea. I'm not actually sure. It's Catherine Fries is the lead author on this paper. I'm not quite sure where Catherine's based. But that new idea that's due to Catherine and her colleagues, it argues that there was a different formation of dark matter particles. So the dark matter didn't condense into particles at the same time as the visible matter.
Right.
It was left as a sort of radiation field within the early universe that took longer to basically flop out into dark matter particles than the protons and neutrons did. They did it within the first 20 minutes or so. But the suggestion is that this radiation field that eventually became dark matter took longer to turn from a radiation field into subatomic particles, even though they're invisible to us. And the reason why that is useful in trying to work out what happened was that it essentially separates the evolution of normal matter from the evolution of dark matter. And that kind of lets you concentrate on the way normal matter came into being, which we think we understand very well, but perhaps opens up new ways that we could look at the models of dark matter if it had a completely separate evolution from the normal matter. I'm not sure I'm explaining this very well, but it is actually a really nice idea. And the team is, I think, the team that's doing this research is giving coined the term a dark Big Bang.
Okay.
They have put a limit on it, a time limit. That dark Big Bang had to happen before the universe reached the age of 1 month. So sometime within the first month, you got the dark Big Bang.
Okay. Now, I did look up Catherine. She's got her own website.
Good.
And it says here on her website that she is the George E. Uhlenbeck Professor of Physics at the University of Michigan.
There you go. Thank you for that.
Yeah.
Thank you. There's one other consequence of this that we might just mention before we turn into pumpkins. That suggests that that dark Big Bang would actually generate very strong gravitational waves that might be detected in today's universe. And so they are concentrating on gravitational wave detection as being perhaps one way of investigating this further.
Fascinating. Okay.
Lovely stuff, isn't it? It's great.
Yeah, it is. Well, we'll, as I keep saying, we will crack it one day. We will figure it out.
And indeed we will.
Hopefully tomorrow.
Probably won't be you and me, but we'll do.
Maybe not. All right. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Okay, we checked all 4 systems and skiing with a go.
Space Nuts.
All right, Fred, we turn it over to the audience, or we turn our attention to the audience as they come up with some questions for us. And our first one today is from Peter. And it's a subject we've never talked about before, except for last week and maybe the week before. And
Hello, Fred and Andrew. This is Peter from Belgium. I was just listening into the last episode and just thinking of a thought experiment. If traveling faster than the speed of light allows you to travel backwards in time from an outside point of view, imagine that you have an observer from Earth. Would you need to be traveling twice the speed of light to actually travel backwards and in time, just at the same rate, but then in reverse on how we currently perceive time on Earth. And so to travel faster back in time, you would just have to travel like 3 times the speed of light. Is this like a linear equation, or are we talking about exponential or another form of relation? Thank you very much, and love the show. Looking forward to the new episode every time.
Thank you, Peter. Faster than light question yet again. We get a few of those. So if you travel faster than the speed of light, which you can't do, but if you could, the theory is that time would go backwards. But if you traveled faster and faster, like 1, 2, 3, 4, 5, 10 times the speed of light, would you travel back in time faster?
So this is it's kind of tachyon theory, is this? That's TACHYON rather than TACKYON. It's not that tacky. It's tachyons are hypothetical particles able to travel faster than the speed of light. Now, as far as we know, they don't exist because relativity is quite firm on the view that to accelerate anything to the speed of light, except light itself, you have to provide infinite energy, and that tends to be a showstopper. Infinite energy is not something we have even today, where energy is a lot easier to come by than it used to be, unless you're in Europe. So the idea of tachyons, exactly as Peter says, is that you will get the phenomenon that, from the tachyon's point of view, time is traveling backwards. Now, I think actually what Peter's hypothesized is probably right, that the faster you travel, the quicker you go backwards in time. It would definitely not be a linear relationship, because nothing in relativity is linear. Everything's usually multiplied or divided by a factor of the square root of 1 minus v squared over c squared. That's the bit that always comes into relativity equations, at least special relativity equations. And that's, for example, why if you just to put it back to something that really does happen, if you are on an object moving at close to the speed of light, if you're on a spacecraft and you point a torch out ahead of you and shine the torch beam ahead of you, your velocity and the speed of light from the torch don't just add, because if they did, they would give you they'd exceed the speed of light. There's something called relativistic addition of velocities. You can look it up on the web, and it once again, it's got that 1 minus v squared over c squared thrown in there that actually means that you never achieve the speed of light. So the velocity addition has, it's not like normal arithmetic. And the same will be true in terms of tachyons. I've never really looked at tachyon theory. I probably should do, shouldn't I, since we get to talk about it quite a lot. Have a look at the equations and see what they look like. But I can imagine already what they look like, just because all relativistic equations have got that in it. Okay. So great question, Peter, and thank you for thinking along those lines.
So the answer was yes. Could have done that.
Yes-ish, yeah.
Yes-ish, yes, maybe. Yes.
So they're not linear. That's the one thing I can say for definite. Right. It's not a linear addition.
Okay. Thank you, Peter. Now I'm going to swipe this question over and put it on your face, because I need to read it in front of me. And this one comes from Gavin in Yass in New South Wales, which is near our national capital of Canberra. I have a question he's got 2 questions, so we'll do them one at a time. I have a question for Dr. Fred regarding a topic seldom mentioned here, space. It appears from photos, etc., that all matter has an angular momentum, which appears to be anti-clockwise except Venus. As all matter was formed from the Big Bang, I assume that the Big Bang also had angular momentum. If space was also formed in the Big Bang, it seems logical that space also has angular momentum. If you think of a bicycle wheel, the hub rotates at a slower speed than the rim. This means that further out you look from the hub, the faster the wheel is turning. If the Big Bang center is everywhere, we are the hub. Same applies to distant galaxies. So What do you think of that idea, Fred?
um, so we don't know if
No,
the
that's a good
universe
answer.
the
That's a
universe
great
has angular momentum. What we do know, and Gavin's correct, certainly in the solar system, most things revolve anti-clockwise as seen from above the Earth's North Pole. And that's because the cloud of gas and dust that formed the planets and the sun actually was rotating. And the sort of theory is that these giant gas clouds that form solar systems, they collapse, and in them you get little whirls and eddies being formed, and it's those eddies that gradually build up to give you a preferred rotational direction, and that's what imparts, as it collapses, the energy of the collapse goes into imparting rotation to the planets, first of all the protoplanetary disk, and then in turn the planets which are formed within that disk. So that's how solar systems work in terms of their rotation. And galaxies are probably somewhat similar, that you start off with gigantic clouds in the early universe that collapse under their own gravity and begin rotating. And so, there's the angular point I'm trying to make is that the angular momentum of objects within the universe comes from processes separate from the Big Bang. They are physical processes that take place in the normal course of events of the universe. So in terms of the universe itself, we don't have any way of detecting whether it's rotating. And if it was, what frame of reference would it be rotating in? Because by the definition of the universe is everything we can see or detect, and that doesn't allow for multiverses, which is a different idea. But in the normal definition of a universe, you wouldn't be able to tell. Only if there are multiverses would you perhaps be able to work out that there is some higher order reference frame against which you could measure the rotation of the universe.
Okay. Have we found any galaxies that are rotating in the opposite direction to what we would consider normal?
Yes, only in the sense that, for example, spiral galaxies almost always are rotating with the spiral arms trailing, and that would be what you call the normal rotation direction. There is at least one that is completely counterintuitive. It's rotating in the opposite direction from the spiral arm trailing model. I can't remember what it's called, but generally galaxies behave well. I should explain though that you don't really know the difference between clockwise and anti-clockwise when it comes to galaxies, because they're all at completely random angles. There are some indications of alignments along the filaments of the cosmic web, which is that sort of background scaffolding structure that we think is what gave rise to the large-scale structure in the universe. I think there are some ideas of alignments of rotation along for galaxies along those filaments of the cosmic web. But yeah, I've looked at that recently. But in general terms, galaxy rotations are pretty random.
Okay. Now, Peter has a second question, and he said recently either the James Webb or Hubble telescopes found a gravitational lens. The lens had 3 images of a distant galaxy. It was observed that a supernova occurred in the galaxy, and the scientists were able to watch the supernova at 3 different times, i.e. the images must have travelled various distances through space due to the curvature of space around the lens. If we have a black hole or neutron star merger which creates a gravitational wave in that distant galaxy, would we detect 3 gravitational waves, i.e. 1 from each image, or would we see only the one? I feel that it would confirm that space bends or light bends, one or the other.
Yes.
Yeah.
Okay. I'm going to quote from a paper in Astronomy and Astrophysics, the main European journal for astronomy. I'm going to quote from that. The quote is as follows: "When gravitational waves propagate near massive astrophysical objects, their trajectories will curve, resulting in gravitational lensing and multiple images. As we observe the waves from each multiple image, their amplitudes will have changed because of the focusing by lensing." So the bottom line is, yes, gravitational waves behave like light when it comes to gravitational lensing, which means that, yes, you might see multiple detections of gravitational waves from the same object if it's lensed by an intervening galaxy or cluster of galaxies, for example. So
There you go.
great question. Yep.
So, yes, the answer is 3 times GW rather than 1 times GW, which was Gavin's
Yes.
little abbreviation for me.
Yeah, that's right.
Okay, so it's
3GW.
3 times GW, Gavin.
Yeah.
That would occur there. All right. Thanks for your question. Thanks also to Peter. If you have questions for us, of course, we'd love to hear from you. You can jump on our website and click on the AMA link and send us a text or audio question that way, or you can click on the send us your voice message on the right-hand side, which just sits there regardless of which page you're on. And it's easy, if you've got a device with a microphone, that's as simple as just pushing the button and saying, "Hi, I'm Fred from Sydney, and I have a question about muscats," or whatever. Yes, that's as easy as it gets. And while you're on our website, have a browse around, check out Astronomy Daily, check out the shop, check out ways of supporting us if you so desire through various means. It's all available on our website and, pretty easy. Fred, and don't forget social media. Lots of people very, very active on the Space Nuts podcast group on Facebook, and it's a lot of fun too. I shamelessly posted a link to my ebooks being on sale for the next couple of weeks, just in case you want, just in case. Well, Fred got your plug.
Yeah, I did.
So-
Yep.
Yeah. Anyway, it's a good fun site. We're done for another week. Fred, thank you so much.
It's a pleasure and great to be back in what is a really very special coury.
It is, isn't it? Yeah. Although we're shrouded in smoke here at the moment. We've had some
You will be. Yeah, you got fires down there. Yeah.
big, hot, windy, dry day last week. We got a big fire south of the city. It's still burning, but they've got it almost under control.
Yeah.
I love the wording they use at the Rural Fire Service around here. If it's not under control, it's being controlled.
Okay.
It's good stuff.
Well, yeah.
All right.
That's right.
Yeah, but we could see it. The grandchildren thought it was amazing. They thought it was a cloud, but it wasn't. It was smoke.
Yes.
Till next week, Fred, thank you so much. We'll see you soon.
Sounds great. Thanks, Andrew.
Fred Watson, astronomer at large, part of the team here at Space Nuts, and thanks to Hugh back in the studio. It's not a studio; it's actually a smoking room or something that he's converted into, a man cave. And from me, Andrew Dunkley, thanks for your company. We look forward to joining you again next time on another edition of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.